Welcome to Chapter 2, Atoms, Molecules, and Ions, Part 4 Screencast. Picking up where we left off last time, then the positive ions, which are called cations, and the negative ions, which are called anions, attract each other and then combine in ratios that give an overall neutral compound. For example, here is a crystal of sodium chloride. For every one positively charged sodium ion, there's a negatively charged chloride ion. Since sodium is +1 and chloride is -1, then one of each gives an overall neutral charge, and then this just repeats itself in all directions, and so any sized crystal of sodium chloride will have equal numbers of the positively charged Na+ and the negatively charged Cl- ions. Now let's do a few examples of this. Na combines with F to form, well, this is pretty similar to the previous one. Na makes a +1 ion. Fluorine makes a -1 fluoride ion. They attract each other, and since sodium is +1 and fluoride is -1, then one of each is a nice neutral balance, so the compound is NaF, a 1-to-1 ratio of sodium to fluoride, and it's called sodium fluoride. We've also seen this one before. Magnesium combines with oxygen. Mg makes a +2 ion. O makes a -2 ion. They attract each other. And since +2 and -2 adds up to 0, a 1-to-1 ratio, or MgO, is what is needed to make a neutral overall compound, and this is magnesium oxide. Now how about when calcium combines with chlorine? Well, calcium makes a +2 ion. Check its column in the periodic table. It's an alkaline earth metal. It would like to lose 2 electrons. And chloride, we've seen before, makes a -1 ion. Now these attract each other, but it requires 2 chloride ions to provide a -2 charge to balance off 1 calcium ion, a +2 charge. And so the attractions are shown, and the formula will be 2 Cl's for every 1 Ca, and this is calcium chloride. How about K with S? Well, K makes a +1 ion. Sulfur makes a -2 charged sulfide ion. These attract, but they don't balance out to a neutral overall charge unless there is a second potassium ion, which is also attracted to the sulfide. 2+ charges balances off 2 negative charges, and the formula for this compound is K2S, 1 sulfur for every 2 potassiums, and it's called potassium sulfide. How about aluminum with oxygen? Well, looking at the periodic table, you can predict that aluminum will make a +3 charged ion. We've already seen oxygen before. It makes a -2 charged oxide ion. These will attract, but not add up to 0. Well, how does nature make this work? What nature does is have 2 aluminum ions, so +3 + 3 gives you a total of +6 charge, and then that balances off 1, 2, 3 -2 charged oxide ions, so 3 times -2 is -6, and -6 and +6 adds up to 0, so the formula for this compound is 2 Als for 1 O, or Al2O3. Now, as a generalization, you might note that ionic compounds are usually formed when there's a combination of a metal, which is likely to form a positive ion, with a nonmetal, likely to form a negative ion. Examples are sodium chloride, NaCl, magnesium oxide, MgO, iron oxide, Fe2O3, and the like. Okay, we'll move on to another topic, and I said, "Give me a wedge, you fool," the golfer is saying. And you might note that wedge is not what he got. He asked for a wedge, but he got a wedgie. And even though those two words are pretty similar to each other, they're not quite the same, and it's important for us to get and use the right name for things. And it's got to be pretty precise, or you sometimes get the wrong thing. So Let's do a little bit with naming for binary ionic compounds, and binary means 2, and now we're doing compounds that are ionic rather than covalent, which we've done before. And like with covalent compounds, we write one of the elements first and the other second, but in this case the metal is written first and the non-metal second. In covalent compounds we didn't have any metals. And as before, we're going to change the ending of the non-metal's name to IDE, but in this case we don't use prefixes because we have a different way of determining how many atoms, or in this case ions, of each type are going to combine. So it's different than with molecular compounds when we have ratios of atoms. Now we have ratios of ions, and we do not use prefixes because we can tell what the ratio will be in a different way. So let's look at a few of these. NaF, Na is sodium, F is fluorine, we call that sodium fluoride. CaCl2, Ca is calcium, Cl is chlorine, we call it calcium chloride. Notice we do not say dichloride because we know a calcium ion will make a +2 charge. We know a chlorine ion will be negatively charged as chloride, and we know there'll therefore have to be 2 chlorides for every calcium, and we don't need to specify the ratio because with our knowledge of chemistry we know what the compound's formula will be just from the name. Similarly with potassium sulfide, we know that potassium will make a +1 ion, we know sulfur will make a -2 ion. We can then go to the formula K2S as we've seen before, and the ratio is fixed by the properties of the elements. We don't need to say dipotassium because we can figure out that this is going to be 2 based upon where potassium is in the periodic table and where sulfur is. And then one more, Al2O3 is simply aluminum oxide. No dialuminum, no trioxide, it's just aluminum oxide. We know aluminum will be a +3 ion. We know oxygen will make a -2 oxide ion. Now that's all well and good if we're dealing with main group elements, but if we're dealing with transition metals, then we're in this part of the periodic table and the charge of the ion is not very predictable. We can presume it's going to be positively charged, but tough to say beyond that. And in fact, this is just a partial listing of a few ions formed by transition metals, and you'll notice there's not a lot of rhyme and reason to where they are in the periodic table, other than of course they're all positively charged. And then you might even notice some elements like chromium and iron, and then there's others that don't show this, but things like copper, that will form multiple possible ions. Copper can make the +2 and +1 ion, iron can make +2 and +3, chromium can make +2, +3, +6, and several others. So quite unpredictable. How do we deal with this? Well, the way we deal with this is by using a Roman numeral to indicate the charge. So for example, to distinguish the iron 2+ ion from the iron 3+ ion, we write Fe +2 as the ionic symbol, and for the name we write iron for Fe and then a Roman numeral 2 to indicate a +2 charge. So how do we specify the name of an iron 3+ ion? Well, iron 3+ looks like that, and the name is iron Roman numeral 3, where the Roman numeral 3 specifies the charge of the ion. All right, now let's tie this in with our naming. How would we write the formula for copper 2 chloride? Well, copper Roman numeral 2 means it's a Cu +2 charge. Chloride is definitely a -1 charge, so we need 2 chlorides to balance 1 copper 2+, and the formula is CuCl2. How about SnO2? Well, Sn is tin, O is oxygen. This would be written as oxide. We know oxide makes a -2 charge, and since we have 2 of them, that's a total of -4. -4 needs a +4 to balance it, and so we would write this as tin Roman numeral 4 oxide. How about iron 3 sulfide? Well, iron 3 means an Fe3+ ion. Sulfide will definitely be a -2 ion. And we're going to need 2 + 3s to balance off 3 - 2s. So Fe2S3 is the formula for iron sulfide. Well, let's do one more for good measure. How would we name Ti3N2? And we notice titanium is a transition metal, hard to predict its charge, but if we know the formula and we know that nitrogen makes a -3 nitride ion, -3 times 2 is -6. -6 has to be balanced by +6. +6 is split among 3 titanium ions, which means each titanium ion is +2 charged, and a +2 charge would be written as titanium Roman numeral 2, and then nitride for the rest of the name. Okay, one last thing now with ions, and just to make life a little more complicated, it turns out that there are a number of commonly encountered ions that are actually made up of a number of atoms bonded together, and then the whole group of atoms has a charge. An example of this is one nitrogen atom often bonds with 3 oxygen atoms. The whole thing ends up having a -1 charge, and this is what we call the nitrate ion, which has the chemical formula NO3 with a -1 charge to the whole ion, and we call it nitrate. There's a number of other ions that are like this, and later in the course we'll investigate why they form the way they do. But for now, you should simply learn a handful of the common, what are called polyatomic ions. Poly means many, and then atomic, so these are many atoms in an ion. And this is actually only a small list. This is from your textbook. There are much more extensive lists of polyatomic ions, but for now I'm going to just highlight the key ones that you should learn: nitrate, carbonate, sulfate, phosphate, hydroxide, acetate, bicarbonate, and ammonium. Notice that almost all of these are negative ions. Ammonium is the example, or the counterexample. It's a positive ion. And these 8 ions you just simply should learn and get familiar with. Okay, let's use a few of them. For examples, what's the formula for potassium acetate? And if you haven't yet memorized them, you can refer to the chart. Acetate is CH3CO2. The whole thing has a negative charge. Potassium would have a +1 charge. So 1 potassium for 1 acetate is the right ratio, and you write it as KCH3CO2. What would we call the compound MgNO3 Well, Mg is magnesium. It's an alkali metal. We know it's alkaline earth metal. We know it's going to make a +2 ion, so we don't need a Roman numeral. NO3- is nitrate, so it's just simply magnesium nitrate for the name. How about going from the name iron 3 hydroxide to the formula? Well, iron Roman numeral 3 means it's a Fe+3 charged ion. Hydroxide is the OH with a -1 charge, so we're going to need 3 negatively charged OHs to balance 1 +3 charged ion, and that's written this way. And notice that the OH is a grouping, so it has to have parentheses around it if there's more than one, and the 3 here refers to the whole grouping. The name of Na2SO4, Na is sodium, SO4, you look it up on the chart, is sulfate, so this is called sodium sulfate. And one more, calcium phosphate. Calcium is Ca, it makes a +2 charged ion. Phosphate is PO4 with an overall -3 charge. We're going to need 3 of the +2s to balance 2 of the -3s. And so Ca, and then parentheses PO4, Subscript 2 is the formula for calcium phosphate.